PowerPoints up on Blackboard. I haven't got all of them yet, that's why I haven't posted the grade yet. So everybody gets there and then I'll do it. Should have got an email on Friday. It said something like speak up, end of term survey for Professor Iqbal's course now open. Did you? You are supposed to fill that up. Of course, I am supposed to encourage you, nothing more than that. Nothing more than that. It's a way for you to tell me, and of course, GT, how things should have been, or what worked really well. So that helps us. Right? In past, it has helped us where students can say, okay, that part didn't quite work out. Helped us syncing lectures with them. Maybe it's still a little out of sync, but it was way out of sync when probably I started teaching it 2 years ago. So it helps us. Students who come after you, they will benefit. If you stick out, it will be helpful to you. You'll have less people bugging you, asking about processes. If we have done our job well here. So today what we're going to do is, we call it student feedback day. We have only one computer, O's computer. Everybody will take his turn on O's computer. Or we can walk to that computer lab. We'll finish 10 minutes early. I'll take you there. It's your call. You log in and do what needs to be done. If you haven't done so. If you have done it already, you get off 10 minutes early. So, helpful. That's why I have to encourage. It has no bearing on your finals because I don't get to see it even before your grades are posted to you. So don't worry about any what you call anything. Simply stated, I don't get to see them before I've posted the grades. Anyways, right? So there are no repercussions for you. So speak your mind. Yes, ma'am.
I think I got 2 emails. One was for the course and one was for the lab. Are we supposed to fill out both?
Both. Right. Yeah, because the other one speaks up on more GDA and how we are doing things. So you have seen that there are very different requirements for lecture and lab. Right? For lab, you have to get your lab notebook up and going. Have your calculations and your reports and all those. Right? So that's something which I wanted to share. And of course, upload your PowerPoints on Blackboard. Right? Yes.
May 4th something.
Pardon? May 4th? Yeah, this will, you have, anyway, we're going to give you 10 minutes to do that today. But your access to that system will close. They will take away that access from all the students who are in standard 15-week courses. I would get it around May 21st when your grades will be posted already. So we looked at this, what happens in a typical CVD process, what are common reactions, and what are the different qualities of film that we desire. So one is confirmation. We are looking at the gross growth model where now we have 2 factors, which is what we call F1 and F2. One is flux, which is just the mass flow, right? And the other flux is what we call the chemical surface reaction, so which is dependent on Ks. So for steady state condition, we say, okay, as much as we provide gets used up. So which would mean F1 equals F2. But it's not always the case. We may be providing more, but the reaction is not going fast enough, right? In that case, it would be HD would be a lot more than Ks, right? In other case, we may be providing less than what reaction wants, right? So reaction is going fast, but we don't have enough of the reactants supplied in there. In that case, this would be the case where Ks would be much faster than Hg. So mass transfer coefficient would be much less than the what you call reaction rate constant, right? So, and that's ultimately will tie up into LPCVD and PECVD. In one case we have high temperature, in another case we have less temperature. So both have different limitations. In a tube we have something what we call plug flow. Plug flow is where reactants, they don't always travel in a plug form. They don't travel in a, what you call, they don't have a uniform boundary. So what we wish to have is this, but what we get is something like this. How would that translate into a reaction?
Non-uniform.
Non-uniform, right? So that's the same thing for oxidation furnace as well. Do we do, okay, what is aware on that? How do I make this concentration close to consistent on the surface of my wafer?
Is plug flow the above or the below?
Plug flow is above, where it
That's
travels.
what we want, right?
That's what ideally we want. What we get is not that. So we have a gas flow rate which is different at different places, and what that results into is non-uniformity, right? So we have to. There are models. How do we get rid of that, or how we cater for that part where there is drag, which causes the boundary concentrations to be different. So as long as we are in this region, we don't have concentration gradient, and we call it laminar flow. Right? How do we create those? So first we have to see the behavior of that tube. And we can get that by running a few wafers a few times. Right? So that tells us how can we measure the end product on a wafer?
Morphometry.
So using those thickness measurement tools, right? So that will tell us the contours, how thickness changes, right? And that will tell us how the gas is behaving in there. So there are number of models that have been produced to understand that. So the idea is that if we have a low Reynolds number, we can have a better flow where the boundary condition doesn't matter. So we want this to be a small number, right? So the small Reynolds number gives us a laminar flow. It's too much information, but only the key point to understand here is Reynolds number defines the flow property. What is a laminar flow?
Flow that's not turbulent.
Flow that is not turbulent, right? And what do we get when flow is not turbulent?
Uniform deposition.
Uniform concentration of reactants, right? When the flow is laminar, what we get is uniform concentration. And what does that result into? Uniform thickness of the film. Make sense? So we want the flow to be laminar.
So what do we actually do to achieve this?
Different things. We can either have this platform to be at an angle facing the flow. Right. We can have multiple wafers placed and the master wafer placed after a few wafers. By that time the flow becomes very consistent. So there is a pattern to the flow of gas which becomes consistent after a few wafers.
Would you get this in oxidation also?
Yeah.
I happened to be, my first wafer was completely non-uniform and the rest.
Very, very non-uniform. The first and last few wafers are very non-uniform. As you get to the center, the gas flow is much more consistent. It's still not laminar, but at least it's consistent because there is now a pattern to the flow of gas. So forget about the much more detail which we would have gone through, but the bottom line is that we want a laminar flow versus a turbulent flow to get consistent gas. So there are few models here that are defined. The boundary layer model defines that your flow and film growth, they have a linear relationship. So your gas flow increases, your film growth increases up to a point where the gas flow becomes, the process becomes reaction dependent. So now even more gas flow will not change deposition because it's reaction limited. Right? So if you encounter this plot, you have to identify regions for what is the limitation at what rate. You should be able to see that. Right? In one case, it's as much gas as you supply will get result into the film thickness. When it gets saturated, it means the reaction rate is not increasing. So we can keep on pumping more gas, but that's not going to change the thickness. That is a reaction rate limited. For those cases where we have the substrates lying on the surface, just to get a laminar flow on every substrate, we have now the issue of the thermal gradient, something like you guys had discussed it in your couple of papers. The thermal gradient is you have heat which is being applied from here and your gas flowing here. So as you go from bottom to top, your temperature is changing, your velocity is changing, your reactant concentration is changing. Right? So you go down, it's decreasing. You go this way, it's decreasing. Similarly, case temperature is more towards bottom, temperature is more towards the end of the flow because by that time the gas has heat up. So when we look at a tube, you have to think of it 3 dimension. You have to think of the heat that is coming from the bottom or maybe from all sides. So there is a gradient for the heat temperature. There's this gas which is flowing, which is colder when it enters, which is much warm when it exits. Right? Where do you place your wafers? It's going to be very different if you have your wafer at this place than you have your wafer at this place. Does it make sense? So what we do is we find sweet spot. In the furnace, we have to find or characterize the film growth properties by doing our experiments. And you guys have seen oxidation furnace, right? Have you loaded those wafers? Right? So, have you or have you not? Okay, you were saying like this, I was not sure. So, I'm just kidding you. So, how do you figure out how far have you, because it's so hot, you can't know inside. How do you know how far you have placed your wafer inside?
There's a mark.
Just where?
There's a mark.
Mark.
There's a mark.
Mark from what?
It's at the center. That's the stick.
Stick?
Rod.
Rod?
Rod.
What do we call that thing?
Rod.
Elephant. That thing which is through which you have this small opening, through which you push it, that's called elephant, and you have rod. It's called elephant because it has one opening through which you are pushing. So all you have to do is you figure out, okay, how much rod should go in, right? That will tell you how far you. So you have to know that where do you place your wafers and what do you get. because of all these variations of temperature, the reactant concentration, change in velocity of the gas, right? So these lines are showing CVT, CVT are showing how they would change in profile.
With CVD, don't you also have to worry about the gradient of the energy you're applying? Because you're applying some sort of energy, like plasma, to these wafers so that the reaction can happen on the surface, right?
Right. So when we are talking about tube, are we talking about LPCVD or PECVD?
I imagine LPCVD.
LPCVD, right? So we are not talking about PECVD.
So what initiates the reaction then?
That again is a different. The issues in PECVD are same. You have a chuck where you are heating it up from the bottom, and we have plasma now on top. In plasma, you are pumping gases, right? So plasma concentration would be different depending on where is your inlet and where is your outlet,
I see.
right? And the temperature you are applying from the bottom, right? So all those things will be similar in that case as well. But in terms of tube, the gas is flowing from one side. But in PECD, you might have different arrangements. You might have gas coming from the top. You might have gas coming from the bottom. We'll see different configuration of PECD gas. So we need to know where do we place our wafer and what do we get out of it. The products are bad. Products, if you want to put silicon, polysilicon, we get silane. Silane is a very toxic gas. It's the same there. The things which come out are also not good. The toxic pyrophoric corrosive, they start burning and they come in the air. That's pyrophoric. Hygroscopic is when it gets in contact with vapor, water vapor. So what we have to do is that we have to know exactly how much is going in, exactly how much is coming out. That tells us, number one, how much is getting used up, tells us when the reaction gets slowed down, because then the concentration of the gases which come out may change as well. Right? So we have to know how much is coming out. What we do, we use MFCs, mass flow controllers, which measure the amount of gases that is coming out. So, no, sorry, MFCs for the gas, how much gas we supply. So what we have is a system where we inject the gas and we have the vapor diluted before it goes into the chamber. And that can be a nitrogen gas, a noble gas, or maybe a reactant species of like hydrogen. And we pump it in the system. So there is all these processes where we have mixing, we have vent, we have circuits that pump different gases at different concentration to get the right mixture. So how do MFCs measure the flow? Now these are reactive species. For one, we cannot do in situ measurement because that will cause reaction, that will cause change in concentration. What does mean in situ? We can't put a probe inside the pipe. We can't probe the gas as they're flowing through. But what we do is we measure something called the change in temperature using a Wheatstone bridge. Yes, I've heard of Wheatstone bridge before. Those who have never heard Wheatstone bridge, they have never heard Wheatstone bridge. It's basically a network of four resistances in which we, right? So we have some reference. One is unknown. So the changes, the voltage drop across that tells us how much was the current flow or the resistance value. So what we do is we want to maintain exact flow. In flow we define in terms of SCCM, which is standard cubic centimeter per minute. So as the gas flows through, into the sensor, out of the sensor, we see the change in temperature after this heating, and that difference tells us the concentration and how fast is it flowing, because when gases flow, they lose temperature. So when you know exactly how much you are heating it and you don't get that, that can tell us the amount of the gas that is passing through. So that's something that we use to adjust the flow. So all processes use high temperature, and then how high is what we used to define a hot wall or cold wall reaction chamber. So hot wall is where we have several substrates coming together, and we have much more range in temperature and pressure. Cold wall is where we don't heat it up, but we provide plasma to do the reaction. And by applying a bias on the substrate, we can make the species to directionally get on the substrate. So in which way we don't get contamination on the walls of the chamber. And in case of hot wall, we get deposition everywhere. So there's much more gases that get consumed in that case. But in case of cold water, we might have much more temperature gradient, resulting into much more variation in the thickness of the film that we get. And in this case, we get one substrate at a time. So a furnace, a tube would be a cold water. A chamber would be, a tube would be hot wall reactor, but a chamber would be a cold wall reactor, right? Where we create plasma, right? So similarly, the LPCVD is what would be generally a hot wall reactor. A PECVD would be generally a cold wall reactor. And in PECVD, what we do is we heat up the holder, not the holder, the carrier, the surface on which we place the wafers. We provide heat there. So when the plasma species, they get there, they get the heat for reaction, and they result into the formation of the film. So these are the configurations for PECVD, where we might have gas coming from one side, we might have gas coming from the center of the chamber, maybe coming from the top with perforation, so to give it a more uniform distribution. You may have gas coming from the outside around a cylinder, right? We may have a single wafer treatment, and we may rotate the wafer for the process. All those cases, we are dealing with those three factors: concentration of the gas, temperature gradient, and what was the third factor? Pressure, right? Because as they flow, the pressure drops. So these are simple configurations for PECVD reactors. Okay, this should have been before, because atmospheric pressure, LPCVD, PECVD, they all have different pressures and different temperatures. And we have seen these numbers that LPCVD has high temperature, right? And PECVD has low temperature, and atmospheric PECVD is a simple reactor which is at atmospheric pressure. In all those cases, we have different advantages and different disadvantages. LPCVD gives us excellent purity and uniformity, and gives you very conformal step coverage. What is the only down with LPCVD? What is the only issue with LPCVD? A major issue? High temperature. Why high temperature is a problem?
Because pressure is
You destroy your device.
It limits the kind of wafers that can go in, right? Limits them. Because if we have metal, in many cases we do have metal, they cannot go in there. So gives us all those good properties, but then at high temperature, what do we do then? So, but it's, and it's low deposition rate, it takes longer to process that. It takes few hours to get to your desired thickness. PECVD is fast, gives you good step coverage, but it has much more contamination issues with it. right? So these are some applications. So it's high temperature oxides, doped and doped silicon, nitrogen polysilicon. In this case, we put insulators over metals because now we would have metals already, and now we would want to put silicon dioxide. We use PECVD, right? So LPCVD and PECVD are more commonly used. Right? So for your application, you'll have to see not only the kind of film you want, but also what you already have on the wafer. Right? We have gold, you probably cannot go LPCVD. So LPCVD is a reaction tube which gives us thin films of polysilicon, silicon dioxide, silicon nitride, and we can play with those with the recipes to get different doping, to get different tensile properties of the film. We can change the thickness as well as the mechanical properties of those films. So typical LPCVD film, LPCVD system, again where we have this furnace type of thing, which is going all the way. We have, it's not visible. We have this mass flow controls. So these are all the valves. We control the values of different valves and how much SCCM we want. Here we define the recipe. Recipe is different levels of temperature, different and related flow of gases. At what temperature you want the flow to start, at what temperature do you want the flow to stop, and for how long do you want it to go. So this is very defined. These are the controls for the heaters, for the heating coils around the what do you call that, tubes. So this is a typical LPCVD system. In PECVD, we pump the gases in, we ionize them by using external power supply. Gives us lower deposition rate. We can control density, resistivity, etch rate, and mechanical properties of the film again. So it has low density films that we apply, which also means the etch rate is higher. When they are lower dense, they can be etched much faster than a film deposited by LPCVD. So if I am given 3 oxide wafers, one with oxide, thermally grown oxide, another with LPCVD oxide, another with PECVD oxide, which one will have highest etch rate?
PECVD?
PECVD. Which one will have lower etch rate, lowest etch rate? Thermal? Thermal will have the highest etch rate. Which one is the lowest etch rate? At this point in time, these things should be very clear to you guys. What's going to happen when you go out and work in the clean room? I'm really afraid of you guys now. Think about it. So, which one gives you most dense oxide? Thermal, right? It consumes silicon right there, and it uses 44% silicon to make 100% of 44 whatever unit to make 100 of silicon dioxide. So it's most dense. Would it be easier to etch or harder to etch? Harder to etch. The etch rate would be smallest. So which one is the the least dense when we draw it?
PECVD.
PECVD. It says right there, somewhere lower density. And it would be easy to etch or not? Easy. Have highest etch rate. So when you have those, they will fall within some range, but you have to know if I get 1000 angstroms per minute with thermally grown oxide, it's going to be much faster for LPCVD or PECVD oxide, most quicker for PECVD oxide.
Which one's higher quality? Is there such a metric for quality? Was on plastics then?
Okay, so what quality metrics we're talking here? Electrical, mechanical? Coverage, so that you have to define, okay, you're talking about step coverage quality, you're talking about tensile strength, you're talking about electrical
The
properties.
electrical properties.
The answer should be clear, the one which is the densest.
So also chemical properties, you're also, I mean, is there any case where you want it easier to etch oxide?
Easier to etch oxide?
Because the whole point of oxide is to shield things, right?
Yeah, but we don't, okay, once you're done, you have made your device, then you don't want it to be etched. You want it to be etched during the process.
That's why I'm saying you don't want it to be easy to etch if possible, right?
If I'm using it as a mask layer, and I have rest of it covered with photoresist, I want it to be etched quick. It has to be etched. Depends on your application. So these are the tools that you have now. So how do you use them is depends on your application.
What's the deal with metallized chips?
So you have metallized chips, anyway you can't put them in high temperature. So you have,
I see.
So you have limited options there anyways too. So you have to do PECVD. And then in PECVD again, you can't go in high temperature process. So there is a limit on how hot can you go, right? What's the highest temperature you can take it to. So now in that recipe is you'll be bound to use those few. So in PECVD, just like any power transfer system, we use supply, which can be RF or microwave, and we transfer into the reactant gas. We transfer into the chamber, and we can get higher deposition rate at lower temperature. So our reaction rate constant is now getting energy. A reaction is getting energy now from that plasma, not from the heat. So this can give us many different combinations of films by adjusting the plasma as well. Gives you better step coverage because they can be used to etch back during deposition, so they give us improved step coverage. They have higher coefficients, sticking coefficients, because they are more reactive. So essentially we have the system where we create plasma, we have the wafers, and then we apply a bias. So the ionic species, they travel towards the wafers. Right? They move under electrostatic field towards the wafer. So in case of microwave, we have magnetic coils to give them direction to go towards the wafer. And we have to pump the products during the reaction. So again, density or stoichiometry is much less in case of PECVD. There can be issues with contamination in case of PECVD, which can result from the products that come out, hydrogen, nitrogen, getting incorporated back into the film. They can ultimately result into film degrading due to outgassing, cracking, changes in threshold voltages of the devices. Hot carrier effects. Hot carrier effects is when charge carriers push through an insulator, basically degrading MOSFETs and having much more inherent charge. So if you get those species which are contamination, they can have electrical as well as mechanical issues with the devices. An example of a batch tool where we can load a bunch of wafers. So this is a mechanical arm which is taking wafers out of these cassettes and loading those wafers in those slots. And we can do a number of wafers in a given time. And they will, after the process, can take out, put them back and get another batch of 5 wafers to go into the process. So these are many, many different types of systems that are doing batch CVD. So this is again an example of a PECVD tool where we have different chambers for different recipes. So now in LPCVD we have dedicated tubes. We do nitride, we do only nitride and dilute. What does that give us? Gives us highly pure films. There's no contaminations. In case of PECVD, we use the same chamber to deposit different films. Why we can do that? Because in PECVD, there's no deposition in the chamber itself. Right? So, if the chamber is clean enough, we still have to clean, but there's no deposition of the material as such, because you have the field applied and your ionization gases, the products are going only on the way. That's not the case in LPCVD. So in LPCVD, we have to have dedicated chambers for the different materials that you want to use there. So again, in this case, it takes a wafer from the cassette, load it up, and do the process. There's a lot, many things different between LPCVD and PECVD. So this thickness, uniformity, so there's much more detailed on that. But what factors we are concerned is thickness, how quickly we can grow, how uniform is the thickness, how pure it is, how dense it is, which is stoichiometry, which will result into the H weight being different. Electrically, how good are they in terms of insulating power? Right? How good they adhere and can they cover steps? So now these are examples to get same thing but through different recipes. So if you see, this is silicon nitride, but we can get silicon nitride through LPCVD as well as PECVD. Both cases, our temperature ranges are different, input gases are different, and we get different properties of the films. Get low stress, insulating. Polysilicon again have only LPCVD, but there we can dope it. We can have recipes where we can dope polysilicon. Can have amorphous silicon. Again, this is done now with LPCVD than LPCVD. Silicon dioxide, many processes to do that, and much variation in the temperature to get there. Right? But their properties are different. Step coverage, H rate, these are all but define how good of a film do we get. Now in this case, silicon dioxide, now we are concerned about the optical properties as well. That what should be the what you call this guy's N is constant for when we do the lipsometry. What is the factor that when the polarization happens?
Diffraction index.
Diffraction index. So that is defined by N. And we need to know this to use the right value for the measurement of the thickness as well. So that can also be factored in. And what kind of film do we get from these different processes? We can dope silicon dioxide. This is glass, and we want to do it to reflow it to cover, to passivate all the devices. And we'll see probably next lecture why do we want to do this. Says now other variations: silicon carbide, diamond like carbon, tungsten, tin dioxide. So it's other materials that I use. So don't get too excited looking at diamond, because these are small crystals, very small. You can't put them on your ring. So these are films which have polycrystalline diamonds, very small crystals of diamonds. Okay, now let's look at some of the examples that we get out of that. We get polysilicon. So we use it for gate electrode, use it for interconnect materials. And essentially, if you want to use it as electrode, you have to heavily dope it. We do it what we call in situ doping. We dope it while it's being deposited. And why not? Why do we want to use polysilicon than metal? Because simply silicon can withstand many more processes. It can go through high temperature process. It has very good interface with silicon dioxide, right? So it can cover many different types of steps. And another interesting thing, we can make what you call silicides, which are the reaction of polysilicon with metals. So why do we want to do that? We'll see. They give us more sticking power. So when you make silicide, they can stick to other materials very easily. So you can react silicon to create another metallic material.
What's an example of a silicide? Like what are the chemical formula?
We'll see that. We'll see that. We'll see many of these tungsten silicide and titanium silicide later on. Okay, how do different polysilicons vary? So, simple example is doped, undoped. Let's see. Says, so we can see after heat treatment what happens to the film. The dope with heat treatment, what happens. So essentially these are grains, and it's like we discussed for deposition. When the deposition starts, we have small depletion sites or small islands which grow ultimately and join each other. So these are all grains, small grains which join each other and give you a film. So that's what we call a grainy structure. And since it's crystalline silicon, but every grain has its own crystalline structure, so we call it polysilicon. It's not amorphous. So you have small regions of crystalline material, but they're interfacing with each other. So their boundaries play a very important role. So it's not just the crystalline property, now it's their boundaries which are also important. So they would have many properties which are similar to single crystal silicon, but because of the grains, they have stresses, they have different resistivity than single crystalline silicon. Right? So simply logic tells us if you have, instead of having a bulk of a complete single crystal which you can dope to make it conductive, now you have grain boundaries. So those grain boundaries would become part of the resistance or the conductance. So you have those extra boundaries now, interfaces where charge carriers have to pass through. Would they be posing hindrance to their flow, or they will be helping the flow? They'll be hindering the flow, right? So they'll be, in undoped form, they'll be hindering the flow now. So that's why it says that it has higher resistivity. At a given open constant, it has higher resistivity than single crystalline, right? So we dope it. We dope it once we are depositing it to make it metallic.
But if they...
Yeah.
Probably have the same question. So why do we use this as an interconnect instead of heavily doped regular silicon?
Okay, hold on. Why do we use this then?
If this has higher resistivity than regular single crystalline silicon, why would we use this as interconnects instead of just heavily doping single crystalline
So
silicon?
you say we should put single crystalline silicon to heavily dope to make the interconnect. How do we create single crystalline silicon? How can we fabricate it?
We grow it, right?
How do we do
I
it?
mean, it's part of the wafer.
Right, but what's the process called?
Krzyzewski.
No, hold on. That's the bulk. That's the bulk you got it. Now you have done some
epitaxy.
Epitaxy. You have to do epi to make it, right? So epi is going to grow it anyway, everywhere.
Oh, I see. So it's that you can't grow single crystalline silicon.
Yes, you can, but it's an overkill. You can get much cheaper polysilicon to get you the same thing.
It's easier to grow and make into interconnects as opposed to.
It's much more easier to get polysilicon.
Couldn't we? I mean, this may be a silly question, but can't we just dope a channel, or is it hard to do that? Like in the wafer itself.
Just one channel.
Yeah, for your interconnects, couldn't you just define your interconnects, mask them with an oxide, and really heavily dope them between your components?
So you're saying instead of doing in situ doping, dope them afterwards?
Yes, or like.
You can, but then if I can do it while I'm growing it, then I can getting two goals met in one process, which is LPCVD for doped polysilicon. Why do I have to do two processes? Once I deposit it and then I dope
I guess
it.
why I'm asking is, why do we bother with this at all instead of doping the bulk wafer? Doping parts of the bulk.
Oh, these are coming on top. These are way above than the bulk.
Oh, I see.
You
It's
have
like a
devices.
multiple in the- okay,
Yeah, you
okay,
have
that makes
devices on
sense.
top, and then
So
you
this is
have
like
the,
the 8th, 9th, 10th, whatever later.
yeah, and this is on top of your silicon dioxide. You have small openings there to approach your source and drain.
I see. Okay,
This
that
is on
makes
top of
sense.
that.
Sorry.
You have to always remember the whole transistor. It's not just.
I'm thinking single layer still.
Even then, you have silicon dioxide. You have to approach just that source region. So you have something which goes only there and touches nowhere else, because that would be short if it touched other
I
things.
see.
You have to define those thin lines. It's not only easy to grow, it's easy to etch also. Polysilicon with grains, the etch rate is much faster when you get rid of polysilicon afterwards. Right? So in etching, we have seen what do we do for etching silicon. What do you use to etch silicon? Pardon?
Buffered oxide.
Buffered oxide
Buffered acid.
to etch silicon?
Oh, that's right. Sorry. Not buffered oxide. Potassium hydroxide.
Potassium hydroxide. So etch rate is much faster with this because now you have so many grains to etch. Right? Multi-directional etch now gets rid of it very quickly.
I see.
Right. So grain boundaries add to the resistance, the resistivity, so which is 2-3 reasons how it happens. So they reduce the overall mobility. So we use polysilicon at many different levels. So these blues are polysilicon. This is, so at the bottom is crystalline, single crystalline wafer, and then you are making devices, 3D devices. Here you have, I think they have a single wall nanotube between these two, which they are measuring. So yeah, this is nanotube between this two polysilicon. So the idea is that you can make 3-dimensional structures with polysilicon and give it, dope it or don't dope it to whatever goal we want to achieve. So it's just one example of polysilicon. It can be doped during growth by adding arsine, phosphine, diborane. Those gases give us different doping as we want. So depending on how much dopant we have with respect to silane, our deposition rate changes. It can, because you're adding those gases can change the growth rate, the grain formation during the deposition. So we can do that, or we can do implantation afterwards to dope it. Right? So this is what is showing that how does it behave for phosphine. As you increase the phosphine, your deposition rate goes down. But if you do the diborane, your growth rate goes really high. So it can grow really fast. What's happening is they have impact on different parts of the grains. So generally the process is what you call pyrolysis, which is thermal decomposition of silane at those high temperatures. So it results into silane which gets absorbed on the surface, but then absorbed silane breaks down, gives hydrogen away, and that turns into ultimately solid silicon on the surface. So depending on your grain boundaries, we will have different density of polysilicon. Right? So highly dense would mean we have much more grain boundaries. Less dense will mean we have bigger grain boundaries. So we dilute the silane to avoid its decomposition before it gets to the substrate. Right? So they depend on the properties of the silane, of the silicon, depend on the temperature as well. Results into low temperature with a smaller grain size. So it's again the same idea that with the length of the tube, we have pressure, we have temperature, we have the concentration of the gas, which changes. So we have to know at every step how is that going to change. The pressure is going to change non-linearly. And we can adjust it by changing the flow rate, this pump speed or how diluted we have it in there. And so it's again diffusion, implantation, or in situ. There are different ways how we can dope it. We can do silicon dioxide CVD as well. Different CVDs give us different. Okay, what was N? Fracture index, right? Which tells us how light would travel through that. Of course, we know the uses. We are going to use it for gate oxide. We are going to use it for field oxide. We are going to use it to make trenches, to fill up trenches, to isolate two devices. We have what we call stacked gate, where we want to have different layers, multiple layers of gate oxide. We have to cover diffusion sources. We have to cover parts of a chip when we are doing a diffusion or ion implantation. We want to cap everything, have to cover everything. So, and we want to passivate everything. So all these uses are for use CVD silicon dioxide for these. So it can have different stoichiometry from thermal silicon dioxide with low density, right? We discussed that it would have low density. And we do some post-deposition temperature processes which densify the silicon dioxide and give us back to the thermal-like properties by annealing, right? The silicon dioxide itself in thermal growth as well is amorphous, so we can anneal it and pack it much more to get close to there.
Are there chemicals other than silicon dioxide that are formed? Are there other oxides of silicon? Like, is there a silicon monoxide?
So SIU explained that there are different stoichiometries. So there can be different oxygen content in silicon dioxide.
I see. By the way, what is SiH2? Is that a natural chemical? Or is that
SiH4 is silent.
What's SiH2? Is that just a radical?
It's
or
just an intermediary.
Okay.
Intermediary step where it would have lost 2 hydrogen. This is just repeat. And of course, just like any film, we want uniform thickness, but in all these mechanical, but what we want on top of that is, for especially silicon dioxide, high breakdown voltage and low K, which results into, which is basically the dielectric constant. Why we need low dielectric constant? What is polarization? Again,
We don't want to create a capacitor.
we don't want to create a capacitor, right? And what does capacitor do?
Stores charge.
Holds charge. How does it hold charge?
If you deposit charge on the
How does it hold charge? Polarization. What's polarization? It comes back the full circle. We started with the polarization definition again. So it's the ability of a material to create dipoles to result into internal shift of charges. So positive and negative charges stay away from each other, right? And that means it's holding that charge, right? In that situation, if we touch it, we're going to have a shock because they would turn back into neutral region and get the energy out, right? So we don't want silicon dioxide to be polarized. Otherwise, it's going to become start acting like a capacitor, right? So high K or dielectric constant defines how much is the capability of a material to create dipoles, right? So we want good amount of dipoles if we are using it as insulated in a capacitor, not for devices. So here we have wanted to be low K, but we have used high K to replace, to have higher thickness, so mechanical problems are not there. So that's a separate issue. But so we want to maintain mechanical electrical properties. We want to maintain index of refraction, H weight, dielectric constant, and electric field breakdown.
So you wouldn't use CVD, silicon dioxide as a gate oxide?
We can do the post processing and bring it down. We can make it more like thermal. We can get it to more like thermal properties after annealing.
But then, okay, then we'll be increasing the K. We want high K for gate oxide, right?
Yeah.
So if you use CVD, it won't guarantee that the K will be good enough.
K would be the same with silicon dioxide. How can you change K for material? You can make high K materials
Yeah.
with higher thickness. But for silicon dioxide, you can't change it,
Okay.
right? But you can deposit it and bring it to the same property, same electrical properties like a thermally grown oxide.
But the density is different, right? For
You can anneal it and get it to close to that thermally grown oxide. That's the whole idea, that we may not have enough silicon to get silicon dioxide. So that's why we do CVD. Of course, there will be trade-off, but we can get much closer properties than thermally grown silicon
For
dioxide.
gate oxide, you would prefer that you grow the oxide then?
Yeah, we want it to be not just thermally grown, we want it to be dry oxide, which is much fine quality, not wet oxide. This you always remember. When you talk about gate oxide, you will be always doing dry oxidation to get that. We don't do CVD, we can do those for field oxide, but not for gate oxide. That has to be very high quality. So again, same things. Temperature, pressure, reactant concentration, and ratio of those, dopant gases, spacing of wafers. These all matter when we are doing CVD. So this is an example of PECVD where you have this substrate spread all over the wafer, all over the chuck, and you close that chamber, you create the plasma. The gas may come from the top or gas may be coming from the bottom, but the reaction happens at the surface and you get the deposition done. So this is a reaction for silicon dioxide. You have silane again reacting with oxygen result into silicon dioxide, it's solid, gets on the surface. The other process is using phosgene, where you get phosphosilicate glass, PSG, which is silicon, a form of silicon dioxide, but it has phosphogene in there. So this is also done by a process called TEOS, which is TEOS is given somewhere. Thermally enhanced.
I think you had it right there on that slide. Tetraethyl orthosilicate.
Yeah, that's tetraethyl orthosilicate. So it's a process called TEOS. So this guy is tetraethyl orthosilicate, which gives you silicon dioxide. So this gives much more better conformality on the surface.
Conformality means better step coverage?
Coverage, yeah. Conformality is always step coverage. Deposition rate can change with temperature and the ratio of silane and oxygen. So if you have temperature going up, you have much more deposition rate. Why do I say temperature going up this way? Because this is 1/T. Where do we see these kind of plots? 1/T, Arrhenius plot. What is Arrhenius plot?
It's a logarithmic temperature versus.
Gives us the relation with temperature. Right? So the Arrhenius relation is of what form?
It's a log of 1/.
D equals D naught exponential of kT by Q. Right? It shows the exponential change with the base value. So this is where we see that change in temperature results into increase in deposition rate. So similarly, when we have theos and oxygen or plasma, or oxygen or ozone. This is O3 and O2. The change is much more with just oxygen than ozone. Right? So the oxygen in this case gives us a tensile strength to a low compressive stress. Right? So the oxide film will be under stress. How can we get rid of a stress in a film? Anneal it. Right? Heat it up and we get rid of much of the stress. So what does ozone do? Oh, yeah, this is basically what is showing that if you do ozone, temperature is increasing this way, now you can get same deposition rate at lower temperature. So you, with the, what does ozone have to do there? What is typical of ozone?
Oxidizer. It's an oxidation agent.
It's what?
It's an oxidation agent. It'll oxidize things.
Right. Things do oxidize. But what is special about ozone?
It's aggressive.
It's aggressive. It's not stable. So it reacts much faster. So ozone is much less stable than oxygen. So we can get the same deposition done at lower temperature. So this gives us high conformity, good gap fill, but at low temperature. So this is example of PECVD, where you are left with these things in there on top of these shaped material. But in this case, on top of them, they are covering everything. Right? So it's poor gap fill with what is called bread loafing. You get this bread type of feature on top. Right? In this case, you don't get that kind of feature. Gives you excellent conformality. Now, the disadvantage is that it has different deposition for different substrates. We don't want that. Right? And it can have water, because ozone is aggressive, it can react with water also and get incorporated into the film. PECVD of oxide can do it at lower temperature with decent filling of gaps. So in this case, instead of that bread fill or still increasing, we are getting full coverage and not getting any voids in the film that's on top of that. So by using a combination of argon and oxygen with silane, we can achieve a bottom-up deposition where things first fill up at the bottom and then they go upwards. So this using of argon results into removal of the material at some places and redeposition. You'll see, you must have seen in deep RIE as well. You want to etch some species as well during deposition. And that etching helps us because it takes away those thin projections which may ultimately become a problem. So it doesn't etch the whole bulk, but it etches those small projections. In this case, it would have taken care of any projection which might have come in this way, but not this actual filling. Right? So some etching species are helpful in deposition because they would not let those projections to grow rapidly. So how do we compare now the PECVD, LPCVD in terms of step coverage? So you want to achieve 100% or above step coverage, but different processes fall at different deposition rate constants. So we want to deposit fast as well, but when we do fast deposition, we don't get good step coverage, right? So it's a trade-off between those two. But LPCVD polysilicon is something which we can deposit fast as well as it can give us good step coverage, right? So we're gonna stay on this curve at least. So there is a trade-off. So either you get fast deposition, then maybe you might be able to live with poor step coverage. But in other case, you might want good step coverage, and we don't care how fast it goes. Right? So this the red is the trend, which essentially all of those fall around. And how do you define step coverage? Step coverage is this angle of incidence with respect to the normal, right? Which defines that how good is our film. And we want this angle to be 0, right? So measure it from a real, what do you call it, high aspect ratio feature. I want this angle to be 0, but we don't get that to be 0. So this is showing that substrate temperature goes up, bombard the atom. So yeah, how do we get rid of this incident angle? How do we get rid of incident angle? We can increase the temperature of the substrate. We can have the etching done while it's happening, bombard the air atoms, which would result into the removal from these edges, which are more than the rest. Or we can rotate the substrate. Rotating the substrate results into a Ravel angle to be the same at every steps, at every point in the substrate. Does it make sense?
How does temperature help get rid of?
If you increase the temperature, you can make the molecules travel. Before they settle, they can travel at high temperature. If in case of low temperature, wherever they get, they're gonna stick there. So high temperature can sort of reflow them during the deposition itself. So this is something which we do on oxide films as well. We reflow them. Then we'll see that when we get to planarization, how do we achieve that? So this is an example of a conformal deposition where the thickness, even at the step, is almost the same, right? So this shows a very good step coverage for the deposited material. It doesn't have pinholes. It's crack resistant. It covers all the variations. This is the reflow of silicon dioxide. And what we get is, after putting it at high temperature, we are reducing that angle. Of course, essentially, we can get this removed if we have an etchant as well in the recipe, but we can get it done in case of silicon dioxide by reflowing it, by annealing it, exposing it to a high temperature. It gets a good step coverage and it gets the stress off the film. Right? So this is something we do with BPSG, borophosphosilicate glass. We saw that reaction. We were getting silicon dioxide and we were getting BPSG as well in that process. Right? So this is again example of temperature versus the angle, how we can reduce that angle with exposure to high temperature. So we are, in all cases, we are reducing the angle down, and this is what we define as our angle. So you see this is fairly high and we are getting it down.